This is a demo for the FIR and Linux combination, right? As we can see over here, there is a very later COSIM and the Renode architecture. But before we get into this, we also want to look at the FIR code filter code itself, right? So let's just take a look at that first. This is the actual code that is written for the FIR filter AXI interface, right? And as you can see, there are of course some standard good practices such as defining parameters for the number of taps, maximum number of samples and the data width. But apart from that, you will see that it's basically providing you with an AXI light interface connection, right? So there are no sort of other inputs, so data in, data out and so on are not provided as inputs to this. What it means is that all of that information comes in or goes out through the AXI light bus. We have defined all our register map offsets inside our code, for example control, status, coef0, coef1 and so on, exactly what I had mentioned earlier. You will notice that for data in, for example, I don't go data in 0, data in 1, data in 2, I just give the starting offset and then say yeah there are 32 words from there, right? And without going into detail on every single bit of the code, a few things that I want to mention. By default, you will see that on reset, the coefficients are initialized to this value 0.25, which is what we expected for the averaging, right? The control start and reset signals, as I had mentioned, are self-clearing, which is why by default they have this assignment in this block which says set them to the value 0. And somewhere inside one of the states, if I actually write, so for example if I write into the control register, the control start could be set to 1, but on the next clock cycle after that, right, it will get set back to 0. It will get set to 1 only on that single clock cycle when it actually reads from W data. After that, in the very next clock cycle, it will get set back to 0 automatically. So both start and reset have that kind of behavior. W1P, write once and write one to pulse and then immediately go back to 0. The status signal has a different behavior. Over here what we have is, it checks whether you are writing and if so it just clears the status bit. It does not check whether it was previously 1 or not, it just sets it to 0, forces it to 0, right. So that is basically a write one to clear. But apart from that, the things are fairly standard. By writing into this address length offset, I can set the length, the number of data values that I need to filter. I can also write into each individual coefficient, right, just populate the values, change them in any way that I want. I can then go in there and and if it's not any one of these addresses, right, it basically by default it says if it is in this range 100 to 1FF, right, take these 5 bits of the right address, take that as an index into the data in array and load that value from W data. In other words, when I write into a particular location, if that address falls in this range, right, which I am checking basically by just looking at this particular part of the right address right over here, right, I can directly load in values into any given location in data in, right. The write response has to be handled similarly, right. I mean this is all very similar to how the original, the smart timer or any other kind of AXI light interface in RTL that we talked about so far. This is how it behaves, right. Now what happens when you want to read back? You can read from control, in which case it will basically give you back this control enable. You can read from status, at which point it will tell you the status done, it will also give you the status ready, right, which is basically related to the state machine that we have internally. You can read back the coefficients. You will notice that you cannot read back the data, right, but what you can do is that if the read address corresponds to this range 200 to 2FF, it will take the value from data out, the output array, and basically send it back on the read data. So in other words, if I try reading back from data in, that is probably going to fail, right. reading back from data out on the other hand will succeed, right? And yeah, that's basically what we have over here, and as long as all of that works. And then we have the actual computation state machine, which basically looks for, have I been enabled and has the control start signal been given, and is the length, the amount of data that is present currently, is it greater than 0? And if so, it basically goes into the processing mode, starts from the first sample, sets the status ready to 0, right, means that it's not ready to accept any new computations at this point, and then actually starts processing, right. And what we have done over here is, like I said, I've just written this for loop. Yeah, we just compute the entire thing in one clock cycle using a for loop over here, right, which, as I said, if you were actually implementing in hardware, would get unrolled into a single computation of 4 multipliers and the corresponding additions. For a small enough number like that is actually also practical, it's not very difficult to do, so it might be a good way of implementing an averaging filter. Right. We take the accumulator, which actually needs to be a 32-bit result, right, because we are multiplying two 16-bit 16-bit values, and we extract the Q15 result, which is basically this Q30, which comes out when you multiply two Q15 numbers, and then discard the bottom 15 bits in order to get the result also in the Q15 format, right. Okay, so this state machine, in other words, goes through and gets activated only when I actually give a start signal. And as we can see over here, once we go into the done state, we make the status ready equal to 1, right. And we also have the done signal, which is when the FIR state is equal to done, the done signal is set to 1, right. And this is the part which is basically a write 1 to clear. This is sent back as part of the status flag, and you can write 1 to status in order to clear it. So the code, the RTL code for this, in other words, looks fairly reasonable. At least this is doing something that we can understand how it would be doing FIR filtering. So let's sort of look at how we can go about doing the entire co-simulation, right. Or rather, it is possible to also just do a CocoTB based simulation first, right. The entire test bench for that is also there as part of this code. And now the test bench for the FIR filter is there as a set of Python CocoTB functions, right. We are going to use CocoTB because after all we are trying to communicate with the AXI light bus. You can see that the tests are fairly simple. We first try to just read, write into a register and then read back from it. We then check the write 1 to pulse signals, right. We check the status, right, whether it is write 1 to clear. And in fact, we also put in some values out here. We actually write a set of values and check whether the averaging filter is in fact working as expected, right. So there are a few tests. You can probably think of adding some more. What we can do, of course, since this is CocoTB based, it has a make file and it will go through and it should run the test bench, right. And yes, sure enough, in this case it tells us that it was able to run all of these, and in this case all these tests that we have over here successfully passed. So that's good. That's how we write any RTL code, right. We first need to write our test bench in Verilog or using CocoTB, something of that sort, which actually allows us to directly test the RTL. But remember, this is only testing the RTL. There is no Renode in the picture right now. There is no processor. It is not actually connected to an AXI light bus. So the next step that naturally comes is, how do we bring that in and connect this to Renode? So let's get to the second part of the demo. So in the Renode part of the FIR filter, we have some part of it which is already set up for the co-simulation. As already mentioned earlier, there is a build folder in which I actually need to go in and compile. I've already done that in this case, so I once again have this live vtop.so, right, which has been created as a result of combining my sim main.cpp, which once again is written in a way such that it encapsulates my FIR filter now instead of my smart timer that I had in the previous example, right, and puts in the Renode agent so that we know that the Renode emulator can now talk to my varilator output. Okay, so far so good. So let's get into my Renode itself, right, and look at the scripts. But before that, there is also the driver that we need to look at, right, and this is a driver corresponding to, which again looks very similar to the kind of drivers that we used for the FFT module. It has, you know, the entire FIR filter memory map that I talked about earlier, the control status length, coefficients, data in and data out, right, and everything else about it is very similar. It has a status register which is a read-only attribute, right. It has the length register which is once again in this case given as a read-only attribute to the Linux side. Remember that I can write into the length register if I want to on the hardware. What this is saying is that from the Linux interface I should not be able to write into the length register and modify it. The expectation is that I change the length register by actually writing data values into it, okay, and we'll see how that happens in a moment. This has something where I can, for example, write in values like this in order to load the filter tabs. So it gives a very convenient user-friendly interface to write new coefficients into the filter tabs. The only requirement over here is you can't write the numbers as real values, right, or floating point values. You have to convert them into integers and write them, and it will be able to directly load those values into memory, right. If you want to, you could also probably change this around so that it can actually take like real numbered or floating point values and convert them into the appropriate Q15 format and send them, but for now that has not been done. Going further, what we have is we can also read out the coefficients, right. Therefore, these coefficients are declared as read-write attributes, and then we have a function for the data in store, right. And this data in store, you will see, does something similar to the coefficient reading because it parses the samples. You can write values into it, right. And now interestingly enough, it automatically after every set of samples that has been written in there, it goes and this part automatically updates the length register. So as far as the driver is concerned, the approach that we have taken is I don't want to directly go in there and modify the length register from Linux, but if I keep on writing data into my data in that attribute, right, it will keep track of what the present length is and keep on increasing that, right, and this is actually an interesting way of doing things, as we will see in a moment when we run it, right. There is a read-only attribute for the data out, which is used for reading back the data and displaying it for you, and the rest of it basically says that, you know, there is like control attributes, the probe, all of this is exactly the same as we saw for earlier device drivers, okay. So once again, this has already been compiled in. I've created a VM Linux image which has this as part of the initramfs, so it should hopefully, when I run Renode, automatically load the module driver. There are a couple of things that I need to see over here. One of them is the overlay, which is being used for the, or rather the REPL, right, the platform part which needs to specify the FIR filter. As you can see, similar to the smart timer, I declare it as a co-simulated peripheral. I give it an address. I have chosen this 7000 2000 as the starting address, and here this part of it is actually crucial. I have given a frequency of 1000, right, and we will see later that if I either give a larger number here, or if I don't give a number here and it defaults to 100 megahertz, the simulation becomes unbearably slow. It can literally run for hours and basically simulate maybe only a few seconds worth of the Linux progress, right? But for now, I'm first going to show you what happens when we give a nice small number like this. Keep in mind that effectively this is almost like saying that my AXI bus is running at like 1 kilohertz, right? A very low speed. The point is, it does not matter because this is bus transactions that we are talking about, right? If at all the bus tries to read from that, it just waits for the Verilog code in order to come back and then say, okay, it has advanced, right? In the meantime, the bus will just basically freeze. It will keep the processor waiting until it has got data back. So nothing else really happens, and Renode is able to advance time much faster. And this happens only when we actually try to communicate with this particular peripheral. At all other times when this peripheral is not active, the Renode simulation runs at its regular speed. There is of course one more thing we need to do, which is our device tree, right? And what I have done over here, once again, just like we did in the case of the smart timer and the FFT, I have gone into the device tree and added the module corresponding to the FIR filter, right? I need to make sure that I give it this address out here. And now here's the thing, I also have the smart timer out here, right? But I have actually not put in a smart timer co-simulated peripheral. You might have noticed that in my FIR, the overlay, the REPL file, it did not have anything for a smart timer, right? And it would be interesting to see what happens when I actually try and access that at some point, okay? But for now, the good thing is, okay, I do have an FIR filter, and now I need to go in and look at my Renode script, and in my Renode script, I actually provide the simulation path corresponding to my FIR filter, right? So everything has been set up properly. I have also added one more line over here which basically tells us to log all accesses to the FIR filter peripheral, and this is a good way of sort of debugging. It helps us to know whether things are working properly, right? Alright, so let's now go ahead and I'm going to just show you the output when we start running the demo, right? The exact process of compiling the driver, compiling the kernel and all is the same procedures as before, and the more detailed documentation will be provided separately. So you can see that everything is set up properly over here, right? It has as usual come up like this. So I'm just going to go ahead and start booting into Linux, and this behaves exactly the same as what it was before, right? First messages start coming up on the UART0, which has been connected directly in the kernel command line, and afterwards UART1 kicks in because that is what is specified as the actual console in the when the once the drivers have been activated, right? So of course it goes through, it takes a certain amount of time. You might notice when you run this that after reaching up to a certain place, it just sort of takes a little bit of time, and then it loads in the full initram fs, and at that point it should actually sort of drop you into a shell, right? Coming to a shell where you can actually type in commands will happen only if you have gone through that entire process of getting a correct initram fs. If it comes only up to this point and then freezes over here, there's a chance that something else is missing, right? So let's just wait until it's done. So you can see that after a little while, right, it basically starts off and it also says running /init as the init process. User space up dropping to shell is actually a message that is there in the init script that I had created and had shown on an earlier lecture. And you might notice that it actually says smart timer platform loading the smart timer and then loading the FIR filter. So in other words, it has loaded drivers for both of these. Whatever it found in the device tree, in other words, it has loaded. Now this is kind of interesting because we know that we don't have a smart timer peripheral. I have not attached anything in terms of RTL, and actually in my Renode platform script I don't even have something corresponding to a smart timer, right. So it's kind of interesting. Let's see what happens. By the way, you might notice a few extra messages like this, about AMBA and so on, deferred probe. Just ignore them, right. Those are some kernel level messages which we can't really get rid of. It's trying to probe devices that it can't find, that's all. So how do we interact with these devices? As usual, it is in sys/bus/platform/devices, right. And you will notice that there is this 7000.smart timer and 7000/2000.FIR filter, both the ones that we loaded, right, the modules that we loaded. I can run ls-mod and find that yes, both of those modules actually exist as things that have been loaded into memory. If I now look inside the smart timer, right, everything seems to be there because the driver has been loaded. It thinks that it can communicate with this particular device. But if I try, for example, to read from it, you will see that the value comes back as 0, right. But more importantly, there is actually a warning coming out on the console out here, which says read double word from non-existing peripheral. Okay. So in other words, finally this is the point at which Renode has found that the peripheral actually doesn't exist. And luckily for us, it just sort of registers a complaint over here. It doesn't crash the system. It just allows it to proceed. As far as the Linux environment itself is concerned, the driver is okay. It essentially failed, right? That read from that location actually failed, but it still gives us back some data because it's allowed to read from that particular location, right? Alright, so now we know that this anyway was not connected. It's not particularly interesting except for just that observation. So instead what I want to do is show you the other one, which is the FIR filter, right. And over here we can see that yes, there are all the things that we defined. There is a control, there is a coefficient, right, there is data in, there is data out, there is this length and status, okay. So this looks interesting. What can we do with it, right? Can I see the value of control? It turns out permission denied. That's because control was basically defined as a write only register in my driver, right. What about status though? This is actually quite clear. It basically tells me that the done signal is 0 and the ready signal is 1, right. In other words, this is the default state of the system. It is ready to accept new data and to start filtering, right, which is why it basically shows up like this. And this part of it, printing it out in this way, is all additional sort of nice aesthetics provided by the device driver, right. The driver could just have printed out as a number, but instead it is also able to translate it into something human readable, because after all the whole point of converting it into a set of files is to make it easier for humans to access and understand what's going on, right. You will also notice that because I had turned on the logging, right, there is this message out here at the bottom which basically says somebody tried to access the FIR filter peripheral and there was a read uint32 from this offset which returned the value 2, which after all was what was printed out. But the interesting thing is, look at this, it says CPU and it shows some strange address out here, right. Now what does this address correspond to? This is the kernel virtual address, right, which we get from IO remap. So it is not the physical address at which the particular peripheral is attached. Instead, that has got mapped into a kernel virtual address, which the kernel then uses, and the driver is, when it finally talks through the kernel, that mapping of converting it back into the physical address so that it can go through is handled internally by the device driver, okay. We don't need to worry about this. We don't really need to know this number. The reason is because every time we load the driver, there is a chance that we get a different value for this address, okay. Alright, so let's go back here. Now this Renode, the monitor also shows a few more interesting things that we can type in over here. For example, it says you could load the coefficients, but let me first look at what is there in the coefficients by default, right? And if I look at this, I can see that it already has these values 2000, 2000 and so on, which hopefully you recall, right, correspond to the number 0.25 in Q15 format. Okay. What about how do I write input data? I can basically do this thing, echo reset, right, because this is again something that is handled internally by the device driver. It looks for this particular string, and if it sees this, it sends the reset signal into the control register, right. This is just something that makes it a bit more convenient for us to use. So I am going to just write reset, in our case, into the data in. Okay, it doesn't particularly do anything, it just sort of resets. What it actually does is it goes and sets the length register back to the value 0. And in fact, if you go look down here, you will notice that there was a write to address offset 8, which corresponds to the length register, and it now has the value 0. Okay. Alright, let us go back and look at this. The next suggestion is to write a string of values, right, all of these values. Where should I write them? Once again into data in. Okay. Now when I write these things, it of course just accepted it, but if I go down to the monitor here, I can see that the first value, which is 10, right, or A in hexadecimal, was written into the address 100. The second value 14, which is 20 decimal, was written into 104. 30 decimal was written into 108, 40 decimal was written into 10C, and 50 decimal was written into 110, and the value 5 was written into register number 8, which is the length register. So in other words, the driver has been written in such a way that rather than you directly saying, okay, this is the number of data values, it calculates the length based on how much data you have written in. Now why is that a nice thing? Because then I can go and do something more like this. I can actually type in echo 60 greater than data in, and as you can see over here, it actually wrote into the next location 114 hex. It wrote the value 60 and it updated the length value to 6. Okay. So I can keep on, I can either write a number of values which are separated by commas, or I can write values one after the other into this particular, just one particular file, and it will keep track of which address it is supposed to write into. Okay. So far there are 6 values sitting inside this. What happens if I look at the length register? It shows me the value 6. What happens if I look at data out? Right now it tells me that all the values are 0. That's because the filtering has not started yet, right? What happens if I try reading back the data in? It's an error because that was defined as a write only attribute, right? So I cannot read from it. What happens if I try writing into data out? That is also an attribute error. Both of those fail. Okay. Alright, so far so good. How do I actually get this to do some filtering, right? What I can do in this case is I echo the string start into the control register, and as you can see down here, there is a write the value 3 into register number 0, which if you go look at the RTL basically corresponds to starting the register, right? We can look at the status and it basically says done 0, ready 0, right? And the data has actually got, yeah. So in fact, the problem is you need to wait for sufficiently long, right? And if you wait, once you have waited for sufficiently long, what you will find is that eventually the done signal becomes equal to 1, right? And after that the ready signal also becomes equal to 1, but what is more important for us is this done signal, right? And if I then look at the data out, I can see that it actually corresponds to these values 2, 7, 15, 25, 35, 45, which if you look through and do the calculations for what is happening, these are the actual averages, right, of the values that you have, right. So the purpose of all of this was to show how we can, in other words, at this point it should be fairly clear that this is not something which just corresponds to, a dummy simulation that I have where in Renode I just put in, let's say, a C block or something like that. I actually wrote RTL, Verilog, and what is being run when I run each of these commands is it's actually directly going and communicating with that RTL, right, which in our case has been very nicely converted into a set of C++ functions and compiled into a library, but still at the end of the day it is actually an RTL simulation that is happening out there, okay. And this is sort of the main power of the co-simulation approach. So there's one last thing that I want to just show. I will not be going into too much detail on this, but it is worth looking at what happens if I change this parameter that we have out here, right, the frequency. So currently what I am doing is I am running the same Renode emulation, but now with the frequency for the co-simulation set at 10 megahertz, right, and you can notice that it is now running appreciably slower. It is definitely far slower than when the frequency was set to a lower number, and the basic reason why that is happening is that the number of times that the co-simulation goes and gets activated and actually needs to run is significantly higher, or is basically much higher, right, because the sort of relationship between the Renode internal frequency and the simulation frequency of the system are now much closer. So you will see that the overall thing runs much slower, it is less responsive, even anything that you type in or any change that you need to make over here will take significantly longer to run, right. So playing around with the corresponding co-simulation frequency might sometimes turn out to be an important requirement for you to get some kind of a reasonable simulation time or emulation time, right. So I'm not going to run through this entire thing, I just wanted to sort of show you, give a feel for how it sort of makes an appreciable difference in terms of the speed, and the rest of the demo would basically remain the same. So I'm going to interrupt it right here. Okay, so what we saw was how we could basically have this FIR filter with an AXI Lite interface, connect it up with a Renode emulation platform, and go through the process of testing out our device drivers, making sure that they actually work with the hardware that we have, right, which is basically modeled directly in RTL, and we don't need to sort of have some other kind of a dummy model just to sort of work on our driver development, right. We can actually work against existing RTL code itself.